And as I mentioned, we do not use high definition maps and we do not use LiDAR. We only use video cameras. And in fact, the vision system that we have been building over the last few years has been getting so incredibly good that it's kind of leaving a lot of the other sensors in the dust. And so actually, the cameras are doing most of the heavy lifting in terms of the perception that you've seen in the car. And actually, it's gotten to the point that we are able to start removing some of the other sensors because they are just becoming these crutches that you start to not really need at all. So actually, 3 weeks ago, we started to ship cars that have no radar at all. So we've deleted the radar, and we are driving on vision alone in these cars. And the reason we are doing this, I think, is well expressed by Elon in this tweet. He's saying, when radar and vision disagree, which one do you believe? Vision has much more precision, so better to double down on vision than do sensor fusion. And what he's referring to is basically like vision is getting to the point where the sensor is like 100x better than, say, radar. Then if you have a sensor that is dominating the other sensor and is so much better, then the other sensor is actually starting to like really contribute. It's actually holding you back, and it's really starting to contribute noise to the former system. And so we are really doubling down on the vision-only approach. And actually in this talk, what I would like to primarily talk about is how we have achieved vision-only control without radar and how we have released this quite successfully so far to the fleet and what it has sort of taken for us to do that. So here I wanted to show a video basically showing what the input of the system is. So we have 8 cameras surround, and these are fairly high definition cameras, and we have 36 frames a second. And you can see that basically you can actually understand a lot about this environment from this input. It's extremely information rich. You're getting a huge amount of constraints, 8 million bits roughly of constraints per second on the state of the surroundings. And so it's incredibly information rich compared to any other sensor you may want to have in a car. And so this is the one that we're doubling down on because this is ultimately where all the difficult sort of scene interpretation challenges lie. So we prefer to just focus all of our infrastructure and development on this. And we're not wasting people working on the radar stack and the sensor fusion stack. We only have one team, the vision team. Now, typically when we talk about vision, the reason people are squeamish about using vision is, and the sort of challenge that almost always is pointed out, is people are not certain if neural networks are able to do range finding or depth estimation of these objects. So obviously humans drive around with vision. So obviously our neural net is able to process visual input to understand the depth and velocity of all the objects around us. But the big question is, can our synthetic neural networks also do the same? And I think the answer to us internally over the last few months that we've worked on this is an unequivocal yes. And I'd like to sort of talk about that. So in particular, the radar API, or like what the radar really gives you, is it gives you a quite accurate depth and velocity measurement. It's a pretty direct measurement of the car ahead of you in very nominal situations. So here I'm showing a random image on the left, and you are seeing the depth, velocity, and acceleration reported by the radar stack for this car. And you can see that it's a bit wiggly on the velocity, so this is some kind of a stop and go scenario. Now, when radar has a good lock on the car in front of you, it's given incredibly good depth and velocity. But the problem with radar is like once in a while, at random, it will give you a dumb measurement and you will not know when that is. And so it's incredibly hard to fuse with vision in our experience. So it might suddenly see a spurious stationary object because of a manhole or because of a bridge, or crossing objects are not very well tracked, or oncoming objects are not very well tracked. And it ends up contributing noise. I'll go into more detail in a bit. But for our purposes, what we want to do right now is we want to match the quality of these predictions using vision alone. So the question is, how can you get a neural net to predict depth, velocity, acceleration directly and do it with a very high fidelity, matching that of radar? So the approach we're going to take, of course, is we're going to treat this as a supervised learning problem. And we need a massive data set of depth, velocity, acceleration on a lot of cars. And we're going to train a large enough neural network and do a very good job at that. That's the standard vanilla approach. And that actually works really well if you do it properly. So here's what it took. So the first component that you need is an incredibly good data set. So, and when I talk about a good data set, I believe it has to have 3 properties that are critical. It has to be large in millions of examples. It needs to be clean. So in this case, we have to have a very clean source of depth, velocity, and acceleration for all these cars. And it must be diverse. So we're not just talking about a single, driving clip of going forward on a highway. We really have to get into the edge cases and mine all the difficult scenarios. And I'm going to show you some examples. And when you have a large, clean, diverse data set, and you train a large enough neural network on it, what I've seen in practice is, in the words of Ilya Sutskever, success is guaranteed. And so let me show you some examples of that. So first of all, how are we going to achieve this data set? So of course, we need to collect training data. The typical approach might be to use humans to annotate cars around us in 3 dimensions. What we found actually works really well is an auto-labeling approach. So it's not pure humans, just like annotating cars. It's an offline tracker, as we call it, and it's an auto-labeling process for collecting data at the scale that is necessary. So we need, again, millions of hard examples. So this is where the scale comes from, is that it's not labeled purely by humans, although humans are involved, it's labeled automatically. So here's an example of some automatic labels we were able to derive for cars.